Hello everyone, our research topic is angular margin centroid loss for texture-independent speaker recognition. My name is Yuheng Wei and I'm pursuing my doctoral degree in the School of Computer Science and Technology of Xidian University in China. The outline of what we want to share is as follows. Firstly, I want to introduce the background of our work. Speaker recognition focuses on extracting identity information about speakers from the speech signals. It is widely used in speech intelligence applications such as identity authentication, personalized speech service, and so on. Generally, speaker recognition is divided into two subtasks: speaker verification and speaker identification. Additionally, depending on whether the speech content is fixed or not, speaker recognition is also branched into texture-dependent speaker recognition and texture-independent speaker recognition. Our work puts attention on the texture-independent speaker recognition, which is a challenge task. A crucial issue of speaker recognition is how to give a unique representation for a specific speaker. Early work uses statistical models including Gaussian mixture maximum model, universal background model, and joint factor analysis, and so on. However, these models are computing expensive when testing. An attractive idea is to find a low-dimensional manifold space to represent a speaker. A vector is such a classical speaker recognition, derived from the factor analysis model. With the rise of deep learning, deep neural networks are widely used as a feature extractor to build such low-dimensional speaker representation, such as D vector, X vector, and so on. Generally, the deep neural network firstly processes the feature sequence at the frame level, and then converts the feature sequence to the feature vector. Finally, we obtain the deep speaker embedding. To obtain the discriminative embeddings, the loss functions play an important role in training deep neural networks. Currently, the loss functions used for speaker recognition could be branched into two types: the multi-classification loss and the pairwise similarity-based loss. Each loss function brings specific strengths and weaknesses. The Softmax loss function is widely used in the classification task. However, it makes speaker embedding inseparable. That is, the speaker embedding remains a large intra-class distance. The under-margin Softmax loss function introduces angular penalty to shorten the intra-class distance and enlarge the inter-class distance. However, it requires a long training cycle, and the classification layer is faced with a dimension explosion problem when there are a large number of speakers in the training dataset. The contrastive loss and the triplet loss requires a complex meaning stringer, and the generalized end-to-end loss makes speaker embeddings inseparable. Our work is inspired by the angular margin Softmax loss and the generalized end-to-end loss. Here, we first introduce them. When using the Softmax loss, the classification layer maps the speaker embedding to the scores corresponding to different speaker classes. These scores are the inner products of the speaker embedding and the weighted vectors. In the angular margin Softmax loss, the length of the speaker embedding and the length of weighted vectors are rescaled to constant values, so that the classification result only depends on the angles between the speaker embedding and the weighted vectors. Then an additive angular margin is used to limit the value scope of the target angle. The generalized end-to-end loss function takes a Rayleigh batch as the input. The Rayleigh batch consists of an equal number of training samples from different speakers. It defines the speaker centroid as the average of speaker embeddings belonging to the same identity, and the similarity between the speaker embedding and the speaker centroid is defined by the cosine similarity with the reliable parameters. During training, the loss function pushes the speaker embeddings to be close to their own centroid and to be far away from other centroids. This is the same as the clustering process. Here is the intuitive presentation of the angular margin Softmax loss and the generalized end-to-end loss. For angular margin Softmax loss, each speak class matches a weight vector, so the dimension of classification layer dramatically increases with the number of speakers in the training dataset, and usually the training circle of the angular margin Softmax loss is long. For the generalized end-to-end loss, the number of speaker centroids is small. However, the speaker embeddings are not discriminative enough. To address the above issues, we propose the angular margin centroid loss. We directly optimize the similarity between speaker embeddings and the speaker centroids. The definition of speaker centroid is the same as that of the generalized end-to-end loss. The proposed loss function has two significant features. First, the loss function directly optimizes the cosine similarity between speaker embeddings and their speaker centroids, and we introduce an additive angular margin to parallelize the angle between the speaker embedding and its corresponding centroids. So this angle is far smaller than angles between the speaker embedding and the other centroids. This effectively improves the intra-class compactness of speaker embeddings. Secondly, we consider the angular distance between different speaker centroids, and we decrease this distance to enhance the inter-class separability. We use a hyperparameter lambda to balance these two terms. Here shows the intuitive presentation of the angular margin centroid loss. It takes a Rayleigh batch as the input and calculates centroids of different speakers. Then the angular margin comprises the speaker embeddings related to the same speaker identity, and the angular distance between different speaker centroids are increased at the same time. This makes the speaker embeddings more discriminative. Lecture we show our experiment details and results. In our experiments, we use library speech dataset. Library speech is a public available speech dataset with rich speaker identity Annotations. We use the training clean 320 subset as the training dataset and use the training clean 100 as their testing dataset. We use the mail file bank allergies as their input of deep neural network and use their fixed length speech segmenters to build mini-batches. Their mean and variance normalization is used to rescale features. Firstly, we compare the proposed loss function with the widely used loss functions for speaker regulation, including Softmax loss, triplet loss, generalized end-to-end loss, and angular margin Softmax loss. Because the value of the angular margin has an important effect on the regulation performance, we tell the different angular margin values. The results show that the angular margin centroid loss could achieve the regulation performance on par with the set of the other loss functions. In the second experiment, we give the detailed angular distributions of both positive pairs and negative pairs on the verification testing set. As shown in figure, the verification performance is determined by the set of the overlap error between the intra-class and the inter-class anchors. The blue arrow represents the anchors between positive pairs, while the orange arrow represents the negative pairs. The Softmax loss and the generalized end-to-end loss have small intra-class anchors, but the inter-class anchors of them are also small. The angular margin Softmax loss and our proposed loss function obtain a good trade-off between the intra-class and the inter-class anchors. In the forward inference process of deep neural network, the angular margin centroid loss deals with the training samples in a millibatch at once, so it is effective. As shown in figure, compared with the Softmax loss and the angular margin Softmax loss, the proposed loss function remarkably reduces the training iterations required by model convergence. A conclusion is given to summarize our paper. In this paper, we aim to enhance the discrimination of speaker embedding for unseen speakers out of the training dataset. To do this, we propose the angular margin centroid loss, which directly optimizes the cosine similarity between speaker embeddings and their centroids. The proposed loss function focuses on their intra-class compactness and inter-class separability at the same time. Experiment results show that the proposed loss function achieves comparable recognition performance with the set of the other loss functions, and remarkably reduces the training iterations required by model convergence.